Hello dear students, welcome back to our virtual classroom. So I hope everyone is fine, and because of this pandemic we are bound to take online classes once again. So anyway, let us start. For this semester, that is the 6th semester, I will be teaching you the discipline specific elective linear programming problem, which is DSE601. You can have a look at the syllabus. The syllabus is here. There are 5 units as usual. The first unit deals with the formulation of LPP and its graphical solution, then convex sets, their properties, slack and surplus variables, and standard form of an LPP. The second unit deals with the simplex method, artificial variables techniques, BGAM method and two-phase method, etc. And the third unit deals with duality, formulation of the dual problems, primal dual relationships, then various methods of solving transportation problems. Okay, and the fourth unit deals with the optimality tests for transportation problem. Also, you will learn about assignment problems, Hungarian method of solution of assignment problems. The fifth unit is something new for me as well. It's game theory. Formulation of games, 2-person zero-sum games, 2-person zero-sum, so solving 2-person zero-sum games with mixed strategies, etc. So anyway, we'll learn these things. So recommended textbook is J.G. Chakraborty by P.R. Ghosh, Linear Programming in Game Theory of Maulik Library, which is quite a nice book. And there are other reference books as well that you can consult. So let us just begin with the basics of this linear programming problem. So from the name itself, you can have one idea that this linear programming problem basically deals with linear inequations or equations. Okay. So anything that is linear. So let us begin with an example so that you can understand better. So LPP does what? LPP is a problem which falls under the wider subject area of operations research. So in operations research, basically we formulate real life problems as a mathematical problem and try to bring out some possible solutions. Okay. So for example, I give you rupees 100 and ask you to buy something for me. Okay, so say I ask you to buy one pen, or not one, say I ask you to buy some pens and pencils. Okay, right? So suppose you buy for me X number of pens and Y number of pencils. Okay, but so what could be the values of X and Y if I do not give you any restrictions? Okay. So suppose, let us bring some more suppositions here. Suppose one pen costs rupees 5 and the pencil costs rupees 10. Okay, so this is rupees 5 per unit. Okay, and this is rupees 2 per unit. Okay, so the prices of the pen and pencils are fixed. Okay, so say suppose I give 100 rupees to the student A. So he or she comes up with a solution that he brings for me say 10 pens and brings for me say 20 pencils. So what is the amount of money that A has spent? The total amount of money, say let us say that is Z. So anyway, if you buy X pencils, X pens and Y pencils, what is the total cost that you incur? The total cost will be Z equal to, it's very simple, 5X plus twice Y, because the cost of each pen is rupees 5 and the cost of each pencil is rupees 2. So the total cost that is incurred when you buy X pens and Y pencils is 5X plus twice Y. Okay, so in the first case for A, what is 5X plus twice Y? It is 5 into 10 plus 2 into 20. Okay, so it's 50 plus 40. Okay, so A has come up with one solution where x is 10 and y is 20, and the total cost incurred is 90, and I am left with 10 rupees. Okay, so A returns 10 rupees to me. Okay, so this is one solution of this problem. So nobody can deny that this is not a solution, it's a solution. Suppose B does something different. B buys 15 pens and only 2 pencils. Okay, so in that case the cost will be 5 into 15 plus 2 into 2. Okay, so it's something like 5 further, so it's 75 plus 4, that is 79. Okay, so this is one more solution that we have got. So B comes up with this solution. So anyway, a lot of money is left. 21 rupees is left. Okay, so say somebody else comes with another solution, that he buys exactly 20 pens for me, and doesn't buy any pencils, because once he buys 20 pens, the total cost becomes this is 5 into 20 plus 2 into 0. Okay, so the total cost is already 100, so he doesn't have any other money to buy more pencils for me. Okay, even then this is a solution, that the student C comes up with 20 pens and 0 pencils. Okay, similarly you can have another solution, that is x equal to 0 and y equal to say 50. Okay, so then this is also a solution. The z will be 0 into 5 plus this will be 2 into 50. So in this case also the maximum cost that can be incurred is 100. Okay, so this is another solution. So you see there are how many solutions of these problems? How many solutions are there? There are several solutions. Okay, there are several solutions, but out of all those solutions, so there are some similarities and differences. In the first two situations, the person who has got the solution has not utilized the entire amount of money that I gave. Okay, whereas in the second two solutions, the person has utilized the entire amount of money that I have given. Okay, so here in the second two cases, the total cost encountered, or total cost or total amount of money spent is maximum. Okay, so in these two cases the maximum amount of money has been spent. Okay, maximum amount of money has been spent. Okay, so that is the difference. In the earlier two cases, the maximum amount of money has not been spent. Okay, even then that is a solution. Okay, but here the maximum amount of money has been spent. This is also a solution. So in the language of LPP, we call such a solution where the maximum amount of money has been spent, or maximum value of z has been obtained, okay, as optimal solution. This is one example. Okay, this when we do the problems, you will see that this may not be the exactly optimal solution. Okay, it depends. Not only reaching z, the maximum value of z will give us the optimal solution. There are some more criteria which need to be filled up. Okay, so for the time being, let's just see that obtaining the maximum value of z, so that is that particular solution will give us an optimal solution. Okay, means I cannot spend more than the given amount 100. Okay, so the maximum possible value of z can be 100. Okay, so but in these two solutions you will see I am getting only pen, or I am getting only pencils. Okay, but what happens if I want both at least? Okay, so in that case I can give you some more restrictions. Okay, so the first thing is that I have given you rupees 100, given rupees 100, I have asked you to buy pen and pencils, and I do not give you any restriction that how many pen and how many pencils you should buy. Okay, the cost of the pencils and this is fixed. Okay, now suppose I give you restrictions, so that I do not want somebody to come to me with 0 pen or 0 pencils. I want that he or she should bring at least some pens and some pencils. Okay, so suppose I give you the restriction that you take rupees 100 and then you buy for me at least you buy at least 5 pen, okay, for me, and you buy at most, okay, or say at least 10 pencils. Okay, so these are the restrictions that I have imposed. Okay, so in the language of LPP, this will be called constraints. Okay, so in the earlier case there were no constraints, right? You are free to buy any number of pen and pencils. Okay, of course one constraint is automatically brought by this restriction, 5x plus twice y, that is the total cost of pencils. Whatever amount of x and y you take, this should not exceed 100. Okay, because you are given only 100 rupees, you cannot buy or you cannot pay the shopkeeper more than that. Okay, you are paying only from the 100 rupees that I have given you. So one constraint in the earlier case is this. Okay, but in this second case, say case 2, I am adding 2 more constraints, that you should buy at least 5 pens and at least 10 pencils. So mathematically, how will I write this? X should be greater than or equal to 5, because I want at least 5 pen. Okay, so the restriction is whatever amount of x and y you buy, it should satisfy x greater than or equal to 5 and y greater than or equal to 10. Okay, so these are the 2 restrictions. So in this case, with this restriction, the first one is not going to be our solution. See, the first one is going to be our solution because x is 10 and y is 20. This is one solution, but the second one is not going to be our solution in this case. Okay, with the second restriction, the second one is not going to be our solution, because here the number of pencils is 2, but I want at least 10 pencils. Okay, so that is not a solution. What about this, x equal to 20 and y equal to 0? This is also not a solution in this case, right? Because I want at least 10 pencils, so 0 pencils is not going to work for me. Okay, x is 0 and y is 50. This is also not a solution in this case, because I want at least 5 pens. Okay, so what will be a solution in this case? One solution is, say somebody called E comes up with one solution, say x is 10 and say y is 15. So this is one possible solution. So in this case, what is the value of z? Z will be 10 into 5 plus 15 into 2. Okay, so what is that? 50 plus 30, that is 80. Okay, so this is one possible solution. Another possible solution, so you can come up with several solutions of this type. Say I take 10 pens and I take 25 pencils. Okay, 25 pencils. So in that case, what is z? Z will be 10 into 5 plus 25 into 2, so that is 100. So here the optimum value of z is obtained. Okay, so this is one optimal solution. Okay, so there may be other optimal solutions as well. Okay, this is not the only optimal solution, there may be other optimal solutions as well. Say for example, x equal to say 15, so 15 values 75, or not 15, say x equal to 16. So if x is 16, then it's z equal to 80 plus another 20 is required. So I can take x equal to 16 and y equal to 10 as another optimal solution, because in that case also the value of z will be 100. Okay, so you see this particular problem has got several solutions when we impose constraints as well. Okay, we can impose other constraints also. So till now what I have got, we have got that you find x and y such that this happens. Okay, so now how can I formulate this type of problem mathematically? Okay, so let us take some more constraints. Suppose I also want that the total cost of buying cannot exceed 80. Okay, so now I give you a restriction that I have given you 100 rupees, but the total cost of buying the products cannot exceed 80. You should not buy anything more than 80 rupees. Okay, so what are the constraints I will get? These are the constraints: 5x plus twice y less than or equal to 80. Okay. Then x is greater than or equal to 5, y is greater than or equal to 10. Okay, and together with that we need these constraints also. These are there in the earlier problems also. I did not mention that x and y has to be non-negative, because you cannot buy -1 number of pencils. Okay, so in the course that we will be doing, in the entire course, every variable will be actually non-negative. Okay, so this constraint is always there in any problem. Okay, so this constraint will be called as non-negativity constraint. Non-negativity constraint. Okay, so as you watch this video, please try to make notes, because I will not be supplying separate notes. You have to take these things down from the video. Okay, so suppose I give you another restriction now, that the total number of products, okay, that you buy should be at or say at most. I have used already at least, so let me use at most say 30. Okay, that means what will be the constraint? The total number of products that we buy. What is the total number of products? I have bought or you have bought x pens and y pencils. The total number of products is x plus y. So this constraint says that x plus y cannot be greater than 30. It is at most 30. So this is another restriction. Okay, this is another restriction of the problem. Okay, right? So this is one example of how this linear programming problem comes up in day-to-day situation. Okay, so there are basically two types of linear programming problem. One is the minimization problem. Okay, and the other is the maximization problem. Okay, so these are the two types of LPP that we encounter. Maximization problem. Okay, so suppose if we want to buy anything, okay, what we do as a buyer, from the perspective of the buyer, we will always want what we want the cost to be minimum, right? We want to buy as many products as possible with minimum cost. That is the normal the requirement as a buyer. Okay, so when we buy anything online also, say something like mobiles and all, so what you do is you compare the costs from various websites, Amazon, Flipkart and all, and you see in which website you are getting a better offer, and you are getting the same product as at a lower cost, or are you getting any sort of discount and all, and then we buy. So as a buyer, we always want the cost to be to be minimum. Okay, as a buyer we always want the cost to be minimum. Okay, so if the problem says something like formulate the problem in such a way that the cost is minimized, okay, then the problem goes to the category of minimization problem. And from the perspective of the seller, the seller will want, what will the seller want? Suppose you are a seller, you will always want that your profit has to be maximized. So we'll want the profit to be maximized. Okay, so whenever your problem has got something to do with profit and all, that has to be a maximization problem. We'll want the profit to be maximized. Okay, so you may ask that what if I want profit to be if I want the profit to be minimized? So in that case there is no problem, your whatever business you are doing, it will just fail. Okay, so the normal economics theory says that the buyer always wants the cost to be minimum and the seller always wants the profit to be maximum. Okay, so that is the usual way of doing the things. Okay, so these are the two categories of minimization, LPP, minimization problem and maximization problem. Okay, so as if we take up our earlier example, so in our earlier example we can formulate it this way: I want to buy some pen and pencil, so I always want the cost to be minimum. So our problem can be formulated this way: minimize z equal to 5x plus twice y. Okay, so that is the total cost if we buy x pens and y pencils. So we minimize this total cost, that is minimize z equal to 5x plus twice y, under what restrictions? Such that say the first restriction that we had given is, say 5x plus twice y is less than or equal to 80, so that you should not spend more than 80. Okay, but you should buy at least 5 pen and you should also buy at least 10 pencils, but the total number of pencils and pens that you buy should not exceed 30. Okay, so these are the constraints, and x and y cannot be negative, so these are always greater than or equal to 0, right? So this is the mathematical formulation of the problem that we have considered. Okay, minimize z equal to 5x plus twice y. Because why it is a minimization problem? Because I am buying something, so I want the cost that, or the money that I spent, has to be minimum. Say I need at least 5 pen and 10 pencils, so why is it necessary to buy 20 pen? It's not necessary, I need only 5. Okay, so there are several solutions, there may be several solutions which take into consideration all of these constraints. Okay, so any values of x and y which satisfy all the constraints, okay, all these constraints will be called a solution of this linear programming problem. Okay, any value of x and y that satisfy all the constraints of the LPP is called a solution of the LPP. Okay, right? And all the constraints means together with the non-negativity constraints. Okay, so we also call this as feasible solution. Okay, feasible solution. So any values of x and y which satisfy all the constraints together with the non-negativity constraints of the linear programming problem is said to be a feasible solution of the linear programming problem. Okay, so let us have a look at one problem that I have taken from the past question paper. Suppose a toy company manufactures two types of dolls, a basic version doll A and a deluxe version doll B. So there are two types of dolls, A and B. Each doll of type B takes twice as long to produce as one of type A, and the company would have time to make a maximum of 200 to 2000 per day if it produces only the basic version. Okay, so basic version is the type doll of type A. Okay, so for the solution we can start with this. Let x number of A dolls be produced. Okay, dolls be produced. Okay, and y number of B dolls be produced. Okay, so please pardon my handwriting. I am writing on an electronic writing pad, so I am learning how to write. Y number of B dolls be produced. Okay, so each okay, now you read these constraints nicely. The company would have time to make a maximum of 2000 per day if it produces only the basic version. Okay, so if the company produces only the type A doll, it can make maximum 2000 dolls per day. Okay, the supply of plastic is sufficient to produce 1500 dolls per day, both A and B type. So here immediately we have got one constraint, that the total number of dolls that can be produced cannot exceed 1500, because to manufacture the dolls you need plastic, and the supply of plastic is just sufficient to produce 1500 dolls per day, both A and B type. So one constraint we have already got, that is x plus y is less than or equal to 1500. The deluxe version requires a fancy dress of which only 600 are available per day. Okay, so that means what? The deluxe version cannot be more than 600 units. Okay, because it requires a dress also. So that dress, only 600 dresses are available, so you can make at most 600 dolls of type B. So y has to be less than or equal to 600. Okay, and if the company makes a profit of rupees 3 and rupees 5 per doll respectively on doll A and B, how many of each should be produced per day in order to maximize the profit? Okay, so what is the profit that is being earned? Profit will be is what we produce x number of A dolls, so profit on the doll of type A is rupees 3, so the total profit is 3x plus 5y. This is the total profit. Okay, total profit is this. So till now we have got two constraints, and together with that we have got the profit function. Okay, so the profit function here is z equal to 3x plus 5y. But however, we have this another constraint left with us. Okay, each doll of type B takes twice as long to produce as of type A. Okay, so that means if we produce y dolls of type B, in the same time we can produce actually twice y dolls of type A. Okay, is it clear? Each doll of type B takes twice as long to produce as one of type A. Okay, and the company would have time to make a maximum of 2000 per day if it produces only the basic version. Okay, so if it produces only type A dolls, okay, let me go to the next page. If it produces only type A dolls, okay, then it can produce 2000 dolls per day. Okay, so in one day it produces x dolls of type A. Okay, in one day it produces y dolls of type B, but in the same time, since the doll of type A type B requires two times more time, okay, than the doll of type A. Okay, so in one day we can produce y number of dolls of type B. Okay, and in the same time we can produce how many dolls of type A. If we instead of making B, if we produce dolls of type A only, then we can make twice Y dolls of type A. Okay, right? So as per these constraints, x plus twice y has to be less than or equal to 2000. Okay, so the number of A dolls that can be produced instead of instead of B is equal to twice y. Instead of producing y number of B dolls, we can produce twice y number of A dolls. Okay, so by equation x plus twice y is less than or equal to 2000. Okay, so now we have got all our constraints. Okay, so the given problem, the mathematical formulation is, so I want to maximize the profit, maximize z equal to 3x plus 5y subject to the constraints, what is that? X plus twice y is less than or equal to 2000, then x plus y is less than or equal to 1500, and another constraint was there. What was that? Another constraint was y is less than or equal to 600. Okay, y is less than or equal to 600, and together with that the non-negativity constraints. Okay, so these are this is the mathematical formulation of the given problem. Okay, so in the next class I will be discussing a few other problems so that you can find it easier to formulate the problems. So in the meanwhile, you keep listening to this lecture, and do let me know if you have any trouble. Thank you.